to discuss cases where the Fourier transforms involve impulses. Let us see the origin of this trouble if we follow the classical rules. So, let me say this some troublesome integrals. We have just now seen an example where in the forward direction we have got a pulse and then we found out the Fourier transform. When we went in the reverse direction, we had to work a little hard to get at the final pulse function. Let us consider another example. We know that delta t has for the Fourier transform equal to 1. Let us find the inverse Fourier transform of this one. We should be able to get delta t. How do we do it? Then we write for the inverse Fourier transform of 1 over 2 pi minus infinity to plus infinity of 1 e to the power of j omega t t omega. And when you try to integrate, you have some difficulty because you have got infinite limits. So, in any case, let us see what this really means. So, minus infinity to plus infinity of cos omega t plus j sin omega t d omega. And once again, sin omega t is an odd function of omega and we are integrating between symmetrical limits. So, we know the contribution from this goes to 0. Contribution from this goes to 0. So, we can write this as 1 over 2 pi minus infinity to plus infinity cos omega t d omega, and once again since cos omega t is an even function of omega, we can write this as 1 over pi and take the limit from 0 to infinity of cos omega t d omega. Now, 1 over pi cos omega t d omega, so far so good, but if you try to integrate, you get minus sin omega t by t, and then when you try to substitute for omega infinity, then you do not know what that amounts to. So, this type of integration does not lend itself to analysis by the classical methods. However, since we started with the inverse Fourier transform of 1, the inverse Fourier transform must lead to delta t. We know delta t has this Fourier transform. So, apparently this whole thing must be equal to delta t. This must be equal to delta t. Now, that is where we have a problem with the classical mathematics, and after the impulses came to be used in analysis of systems, then after their usefulness is recognized, mathematicians have developed a branch of mathematics called the theory of distributions, with the help of which the analysis of the mathematical methods using impulses are put on a more rigorous basis, but we will not go into that. We will, however, make use of certain results of that and put them down here, so that we will use them for our further work. Basically, then we have some important results which I will list them out, and these results which we will make use of in our future work. First of all, limit as t tends to infinity of sin omega t by omega will be pi delta omega. It can be explained on the following basis. Sin omega t by omega, how will it look like? So, this will be equal to t, the height equals t, and the first 0 occurs when omega t equals pi, or t equals pi by, or this is sin omega t by, this is with respect to omega, or omega equals pi upon t. Now inquire as what happens when t becomes larger and larger. When t becomes larger and larger, sin omega t by omega, the function becomes this is pi upon t. So this first loop becomes smaller and smaller, but the height goes up. And we have already seen that the area under this curve of this is, as far as for the positive side is concerned, the area equals pi by t times t into half, therefore this is pi by 2, and on the other side is pi by 2. That means the area under this curve is pi. The area under this curve is pi no matter what t you use. So as the area from minus infinity to plus infinity of this is pi, and as t becomes larger and larger, this loop shrinks, and then you have a very large amplitude, and the first loop becomes 0. That is essentially the character of an impulse. And since the area under the curve is pi, then it is an impulse of value pi, and the impulse is situated at omega equals 0, because that is where you have a spike. So we can justify this on this fashion, in this fashion, that sin omega t by omega as t goes to infinity is tends to the limit pi delta omega. Similarly, we can have 0 to infinity of cos omega t d omega equals pi delta t. That you have seen from this. We have earlier come to this. We got into difficulty 0 to infinity cos omega t d omega. What is it? What does it mean? It is pi times delta t. We did not know how to derive this, but we can assume this relation. Similarly, we have 0 to infinity cos omega t dt. After all, we have changed the variables here. This must be pi delta omega. And two more relations are useful. 0 to infinity sin omega t dt equals 1 over omega, and 0 to infinity sin omega t d omega is 1 over t. We assume these relations in our work when we derive the Fourier transforms of functions whose energy content is maybe infinite, may not be finite. So these four relations are important for us. We will take this to be true in our further work. Okay. We will make use of this, as I said, in our further work, but just as an example, we will consider just one particular case. Let us take a simple example now to illustrate this, these relations. We will take f of t to be a DC quantity equal to 1 for all t. So that means f of t is a constant 1. F of j omega for this is obviously from minus infinity to plus infinity of f of t e to the power of minus j omega t dt. Now e to the power of j omega t can be written as cos omega t minus j sin omega t, and once again we can make use of the symmetry relation, and the cos sin omega t term will be this is minus infinity e to the cos omega t minus j sin omega t dt, because f of t happens to be equal to 1. And the contribution of this will be 0 because it is an odd function and we have symmetrical limits. Therefore, I can write this as only integral involving cos omega t. Now I take from 0 to infinity of cos omega t dt, and I introduce a 2 sign because 2 here, because instead of integrating from minus infinity to plus infinity, I am integrating 0 to infinity. And now cos omega t dt integral from 0 to infinity is pi delta omega according to what we had already seen. Therefore, this is 2 pi delta omega. So the Fourier spectrum for this is f of j omega. You have an impulse of magnitude 2 pi at DC. This is what we should expect. This is a pure DC term. Therefore, you have only a DC component here and no other components. And at the DC, we have a finite amplitude for the voltage. Therefore, you have an impulse function. That means we are no longer, even though we are talking about coefficient density now, this coefficient density is infinite because there is a definite non-zero amplitude at DC Therefore, the coefficient density is going to be infinite and it has got a magnitude equal to 2 pi. We will develop this theme further when we take about other periodic signals. So, in this lecture therefore, what we have done so far is we started with the concept of energy in a periodic signal. We said when we talk about a periodic signal with finite energy, it is no longer fruitful for us to talk in terms of power, because the average power over infinite interval goes to 0. Therefore, we can talk only in terms of energy available from the signal, and what we mean by energy available from the signal is, if this signal is a voltage signal, if it is given to a 1 ohm resistor, what is the total energy dissipated in that 1 ohm resistor from minus infinity to plus infinity is what we call the energy available from the signal. And this energy available in the signal resides in different frequency bands by different amounts. Therefore, we saw that if we integrate from minus infinity to plus infinity, the energy density which is given by f j omega squared, integrate it with reference to omega and divide by 2 pi, because this energy density is in terms of frequency in hertz cycles per second, that will give you the total energy. And this we said is also referred to as Parseval's theorem. Then we discussed the possibilities of extending the Fourier analysis to signals whose energy content is not finite, and in that context we started with some interesting relations involving sin theta by theta functions, and we familiarized ourselves with sine integral, and then we put down some results here which are sanctified by the distribution theory in mathematics, which we cannot prove by classical methods. We assume these results, and making use of these results we tried to find out the Fourier spectrum of a pure DC quantity and came up with the result which is quite perhaps could have been quite obvious, that this particular signal has only one frequency component, and that is a DC, and therefore you have only one, the lines, it becomes a line spectrum once again in the Fourier transform also, but in the coefficient, there is a coefficient which is non-zero, therefore the coefficient density has got to be infinite, therefore we have a delta function and the coefficient density is 2 pi delta omega, and the density occurs at 0. And so we can expect that when we talk about periodic functions, in the line spectra, the magnitudes are going to be infinite involving delta functions. More about this in the next lecture.